There was a moment, so brief it defies imagination, when the entire universe was smaller than a single grain of sand. And then, in less than a blink of cosmic time, it exploded outward, stretching space itself faster than the speed of light. This wasn't just the Big Bang, it was something even more extraordinary, a runaway expansion we now call cosmic inflation. For a fraction of a second, the universe grew from a speck to something unimaginably vast, leaving behind echoes of its violent birth that we're still deciphering today. What if I told you that this fleeting instant holds the answers to some of the most profound mysteries in existence? Why does our universe have galaxies, stars, and planets instead of just empty chaos? What strange forces were at work in those first moments, shaping everything we know? And perhaps most tantalizing of all, what clues are still hidden in the fabric of space itself, waiting to be uncovered? The cosmic inflation era didn't just create our universe, it left behind puzzles so deep that even the brightest minds are still piecing them together. In this journey, we'll explore 25 of these mind-bending enigmas, questions that challenge our understanding of reality itself. From bizarre relics of that hyper-expansion to the eerie fine-tuning that made life possible, each mystery is a thread in the grand tapestry of the cosmos. Some might rewrite the laws of physics, others could reveal whether our universe is utterly alone, or just one of countless others in a vast multiverse. And as we peel back the layers, you'll see how these ancient echoes from the dawn of time still shape the universe around us today. This isn't just a story about the past. It's the key to our future, so let's begin. Imagine a universe so unstable, teetering on the edge of an unimaginable transformation. What could possibly trigger such an explosion of space itself, stretching reality beyond comprehension in less than a trillionth of a second? The mystery of what ignited cosmic inflation isn't just a question about the past, it's a crack in the foundation of physics, one that challenges everything we think we know. Some scientists believe it all started with quantum fluctuations, those tiny, unpredictable ripples in the fabric of reality. At the smallest scales, particles blink in and out of existence, and in the early universe, these flickers may have been amplified into a runaway expansion. Others propose an even stranger idea: false vacuum decay. Picture the early cosmos as a superheated kettle, balanced precariously in an unstable state. Then, with a single cosmic jolt, it collapsed into a lower energy state, releasing an unstoppable surge of energy that stretched space-time like taffy. But here's the catch: we don't have a smoking gun. Inflation happened so fast, so violently, that all traces of its trigger were likely erased. The only clues we have are the faint imprints it left behind: ripples in the cosmic microwave background, the large-scale structure of galaxies. These echoes hint at something monumental, but they don't tell us what flipped the switch. Without knowing what started inflation, we can't be sure if it was a one-time event, or if it's still happening in distant corners of the universe, birthing new realities beyond our own. This mystery isn't just academic. If we could uncover the true trigger, it might reveal whether our universe is inevitable or a cosmic accident. Was inflation destined to happen, written into the laws of physics? Or was it a fluke, a random quantum burp in an otherwise silent void? The answer could change everything, because if inflation had even slightly different conditions, galaxies might never have formed, stars might never have ignited, and we wouldn't be here to ask the question at all. The moment inflation began might be one of the most explosive events in history, but how long did it actually last? Was it over in less than a trillionth of a second, or did it stretch on just long enough to sculpt the cosmos we see today? This isn't just a question about timing. It's a missing piece in the puzzle of our universe's earliest moments, one that could rewrite the story of everything. For decades, scientists assumed inflation was a lightning-fast event, over almost before it began. But recent theories suggest something far stranger, that inflation might have pulsed in waves like an engine stuttering to life before roaring into motion. The problem is, inflation left no direct clock, no cosmic timestamp to measure its duration. All we have are the aftereffects, the way galaxies cluster, the faint wrinkles in the cosmic microwave background, the strange uniformity of space itself. These clues hint at inflation's power, but they don't tell us how long it burned, and that uncertainty changes everything. If inflation was too brief, it wouldn't have smoothed the universe enough to explain why the night sky looks the same in every direction. Too long, and it would have erased all the tiny quantum ripples that eventually grew into galaxies. There's a Goldilocks zone, a precise window where inflation lasted just long enough to create the conditions for stars, planets, and us. But was that window a fraction of a second, a few heartbeats, or something even more bizarre like multiple bursts of expansion separated by pauses? The stakes are higher than they seem. If inflation didn't last exactly the right amount of time, our universe might have been left a featureless void or torn apart by runaway expansion. Every galaxy, every atom, every moment of existence hinges on that unknowable sliver of time. And until we find a way to peer deeper into those first instants, this mystery will keep us guessing. Was our universe's birth a fleeting spark, or a slow, deliberate unfurling of reality itself? One of the strangest riddles about cosmic inflation isn't how it started, it's how it stopped. Think about it. Space itself was stretching faster than light, yet somehow, this runaway expansion slammed on the brakes with pinpoint precision. If it had ended even slightly differently, the universe as we know it wouldn't exist. This is the graceful exit problem, and it's so baffling that even the most brilliant cosmologists still debate it. One leading theory suggests a phase called reheating, where the energy driving inflation suddenly transformed into the searing heat of the Big Bang. Picture a stretched rubber band snapping back, except here, the snap didn't just release energy, it repurposed the very fabric of space-time, filling the newborn universe with particles and light. But there's a catch. We've never observed direct evidence of this reheating. The cosmic microwave background, our closest window to that era, shows only the aftermath, like finding ashes but no traces of the fire that made them. Another idea proposes that inflation didn't truly stop everywhere. Some regions of space might still be inflating eternally, spawning infinite pocket universes while our own became stable. This would mean we're just one bubble in a frothing multiverse where the rules of physics could be radically different elsewhere. But without a way to detect these other bubbles, the theory remains as speculative as it is thrilling. The stakes couldn't be higher. If inflation ended too abruptly, the universe would have been left a chaotic, uneven mess, too slowly, and matter would have scattered too thinly for galaxies to form. The precision of this transition borders on miraculous, like a skydiver hitting the ground at exactly the right speed to land safely every single time. So how did nature pull it off? Until we uncover new clues, perhaps hidden in gravitational waves from the universe's first moments, this mystery will keep us questioning whether our cosmic home was shaped by law, luck, or something even stranger. The universe didn't inflate smoothly, it crackled with tiny imperfections, quantum ripples so small they'd vanish in a heartbeat under normal circumstances. Yet these faint wrinkles, born from the chaos of the earliest moments, became the seeds of everything we see today. How did subatomic flickers grow into galaxies, clusters, and the vast cosmic web? And why do these primordial density variations still leave scientists scratching their heads? Here's the puzzle. Inflation should have stretched space so thoroughly that the cosmos became perfectly even, like smoothing out a crumpled sheet. Instead, when we look at the cosmic microwave background, the faint afterglow of the Big Bang, we see temperature variations, patches where matter was ever so slightly denser or sparser. These imperfections are minute, just one part in 100,000, but they are the reason stars exist at all. Without them, gravity would have had nothing to grip, leaving the universe a featureless void. The leading explanation ties back to quantum mechanics. During inflation, space wasn't just expanding, it was a bubbling quantum foam where particles and energy flickered unpredictably. When inflation ended, these quantum fluctuations got frozen into space-time like footprints in suddenly hardened concrete. Over billions of years, gravity amplified the denser spots, pulling in gas and dust until galaxies ignited. But here's where things get strange. The patterns in the cosmic microwave background don't always match predictions. Some regions show unexpected clumpiness, while others are eerily smooth, as if an invisible hand tampered with the blueprint. Even more baffling is the so-called axis of evil, an alignment of anomalies in the CMB that some theorists argue hints at a pre-inflationary structure, a relic from whatever existed before our universe. Could these variations be scars from a previous cosmic cycle, or evidence of forces we haven't yet discovered? The answer might lie in gravitational waves from the dawn of time, faint ripples that could carry clues about inflation's quantum origins. Until then, these primordial wrinkles remain both the architects of our cosmos and one of its deepest enigmas, proof that even in the vastness of space, the tiniest details can shape everything. Among the most perplexing relics predicted by cosmic inflation is a particle that should be everywhere, yet remains utterly missing. Magnetic monopoles, hypothetical entities with a single magnetic pole instead of the usual pair, were supposed to flood the universe during its violent expansion. Their absence isn't just a curiosity, it's a gaping hole in our understanding, one that either forces us to rewrite the rules or accept that the cosmos is hiding something extraordinary. The case for monopoles begins with grand unified theories, which suggest that in the extreme heat of the early universe, the fundamental forces electromagnetism, the strong nuclear force, and the weak nuclear force were merged into one. As the cosmos cooled and these forces split apart, defects should have formed in spacetime's fabric like cracks in ice. These defects would manifest as monopoles, particles with a north or south magnetic charge, but never both. Inflation's rapid expansion should have scattered them everywhere, leaving behind a universe littered with these magnetic oddities. Yet after decades of searching, from deep underground labs to cosmic ray detectors, not a single confirmed monopole has been found. This isn't just bad luck, it's a crisis for physics. Either our theories about the early universe are catastrophically wrong, or inflation did something far stranger than we realized. Some scientists argue that inflation diluted the monopoles, stretching space so thoroughly that they became impossibly rare. Others propose that monopoles were never created in the first place, hinting that grand unification happened differently or not at all. The implications are staggering. If monopoles don't exist, it could mean the forces of nature never truly unified, challenging the dream of a single theory of everything. Alternatively, their absence might signal that inflation erased more than we thought, wiping out not just monopoles but entire chapters of cosmic history. Or perhaps they're lurking just beyond our reach, cloaked by dimensions or energies we can't yet probe. This missing particle mystery isn't just about filling a gap in a textbook. It's a battle between two possibilities. Either we've misunderstood the universe's most fundamental forces, or nature played a trick on us, hiding clues in plain sight. Until we find them, or prove they were never there, the case of the vanishing monopoles will haunt physics, a ghostly reminder of how much we still don't know. One of the most mind-bending consequences of cosmic inflation is how it rewrote the rules of cause and effect in the early universe. Before inflation was proposed, scientists faced the infamous horizon problem, a paradox that threatened to unravel cosmology itself. Here's the puzzle. When we look at the cosmic microwave background in opposite directions, those regions appear nearly identical in temperature and structure. even though they were supposedly too far apart for light or heat to ever travel between them. It's like walking into two identical bakeries on opposite sides of the planet and finding the same warm loaf of bread fresh from the oven at the exact same time without any possible connection between them. Inflation solved this by stretching space so rapidly that regions now billions of light years apart were once in intimate contact, allowing them to equalize before being violently separated. But this fix came with a cosmic twist that no one saw coming. If inflation expanded space faster than light, how did information or influence ever propagate across the universe? Normally, nothing can outpace light, but inflation essentially cheated by stretching spacetime itself, not moving matter through it. This means that while two regions appear causally connected in the past, the mechanism defies our everyday intuition about how causes must precede effects. The deeper mystery lies in what this tells us about the universe's true scale. Inflation suggests that the observable cosmos, everything we can see, is just an infinitesimal fraction of the whole. The real universe could be exponentially larger, with countless regions forever beyond our horizon, each potentially harboring different physical laws or even alternate versions of reality. Some theorists argue that this challenges our very definition of the universe, blurring the line between what's knowable and what's fundamentally hidden. Even stranger, certain anomalies in the cosmic microwave background hint that inflation might not have been perfectly uniform. Some patches of sky show statistical quirks, like the infamous cold spot, that could suggest collisions with other inflating bubbles in a multiverse. If true, it would mean that while inflation solved the original horizon problem, it opened a Pandora's box of questions about what lies beyond our cosmic horizon, and whether the universe we see is just one thread in an unimaginably vast tapestry. One of the most startling predictions of cosmic inflation is that our universe should be perfectly flat, not in the sense of a sheet of paper, but in the way space itself curves, or rather doesn't. Imagine drawing a triangle on a flat surface. Its angles add up to 180 degrees. Do the same on a globe and they exceed that. Now scale this up cosmically. If the universe had positive curvature, like a sphere, parallel beams of light would eventually converge. Negative curvature, like a saddle, would make them diverge. Yet every measurement we've taken, from the cosmic microwave background to the large-scale distribution of galaxies, suggests space is dead flat with a precision that defies coincidence. This flatness isn't just a quirk, it's a direct consequence of inflation's relentless stretching. Picture a balloon inflating to the size of the Earth. Any tiny wrinkle on its surface would vanish, appearing flat to an ant crawling on it. Similarly, inflation stretched the universe so enormously that any initial curvature was smoothed to near perfection. But here's where things get thorny. Recent data from the Planck satellite reveals a slight but tantalizing deviation from perfect flatness, a whisper of curvature that lingers at the edge of statistical significance. Some researchers dismiss it as noise, while others wonder if it's a crack in inflation's flawless facade. The debate hinges on omega, the ratio of the universe's actual density to the critical density needed for flatness. Inflation predicts omega should equal 1 with near infinite precision. Planck's measurements hover agonizingly close, around 0.9999, but that tiny gap leaves room for doubt. Could it mean inflation wasn't quite as all-encompassing as we thought? Or does it hint at something deeper, like an undiscovered energy field that tweaked the curvature? Flatness isn't just geometry, it's a cosmic balancing act. If the early universe had been even slightly denser, it would have collapsed back on itself in a big crunch. Slightly less dense, and matter would have scattered too thin for galaxies to form. The fact that we're here at all suggests an almost impossible fine-tuning, one that inflation elegantly explains, but only if the flatness is absolute. That Planck's data leaves the door even slightly ajar, forces us to confront an unnerving possibility. What if inflation didn't erase all traces of curvature and our universe is subtly, fundamentally shaped in ways we've yet to grasp? The implications ripple outward. If the universe isn't perfectly flat, it could mean we're seeing evidence of a pre-inflationary structure, or that multiple episodes of inflation left faint wrinkles in spacetime. It might even challenge the idea of an infinite universe, suggesting that space, while vast, could still curve back on itself in ways too subtle for current telescopes to detect. Until future missions refine these measurements, the flatness mystery remains a quiet challenge to our cosmic certainty, a reminder that even the smoothest surfaces might hide invisible depths. One of the most explosive ideas to emerge from cosmic inflation isn't about our universe, it's about what might lie beyond it. If inflation didn't just happen once but continues eternally in some regions of space, it could be spawning an endless sea of universes, each with its own laws of physics, its own history, even its own version of reality. This is the multiverse hypothesis, and it's not just science fiction, it's a legitimate, if hotly debated, consequence of the math behind inflation. Picture a boiling pot of water, bubbles forming and expanding at different rates. In eternal inflation, spacetime behaves similarly. Regions where inflation stops become pocket universes like our own, while others keep stretching indefinitely, birthing new bubbles ad infinitum. Some of these universes might have stronger gravity, making stars burn out in seconds. Others could have no weak nuclear force, preventing atoms from forming altogether. The unsettling implication: our universe's life-friendly laws might not be special, just one random outcome in an unimaginable cosmic lottery. This idea gained traction with string theory, which suggests there could be 10 to the 500 possible configurations of physics. If each bubble universe locks in a different set of these stringy rules, it would explain why we find ourselves in one where conditions allow galaxies, planets, and life. But here's the catch: if the multiverse is real, how could we ever prove it? Most of these universes would be forever beyond our cosmic horizon, their light too distant to ever reach us. Critics argue this makes the theory untestable, more metaphysics than physics. Yet some scientists are hunting for clues. If our universe collided with another bubble during inflation, it might have left scars in the cosmic microwave background, odd patterns or temperature anomalies. Others propose that gravity waves from the early universe could carry echoes of these collisions. So far, no smoking gun has been found, leaving the multiverse in a limbo between tantalizing possibility and untestable speculation. The debate cuts to the core of what science is. Supporters see the multiverse as an inevitable extension of inflation's math, a universe-generating mechanism so powerful it couldn't have made just one. Detractors call it a retreat from empiricism, a theory that explains everything but predicts nothing. Even legendary physicists are divided. For every voice championing the multiverse as the next Copernican revolution, another warns it risks turning cosmology into a philosophical guessing game. What hangs in the balance isn't just academic, it's our place in reality. If the multiverse is real, humanity becomes a statistical inevitability in an infinite ensemble, not a privileged observer. If it's not, the fine-tuning of our universe remains an unsolved riddle, begging for a deeper answer. Either way, the question forces us to confront the limits of knowledge itself. Are some truths forever beyond our reach, or will future breakthroughs pull back the curtain on realities we can't yet imagine? Cosmic inflation was supposed to solve one of the most vexing problems in cosmology, the Big Bang singularity, that infinitely dense, infinitely hot point where all known laws of physics break down. By proposing a rapid expansion before the traditional Big Bang, inflation seemed to sidestep the singularity, replacing a mathematical impossibility with a dynamic process we could actually study. But here's the uncomfortable truth: inflation might not have erased the singularity at all. Instead, it could have just kicked the can down the road, leaving us with an even deeper mystery lurking in the universe's first instance. At the heart of this puzzle lies gravity's most brutal limitation. Einstein's equations of general relativity predict that if you rewind cosmic expansion far enough, everything collapses into a singularity. Inflation stretches space-time so dramatically that it pushes this mathematical nightmare further into the past, but it doesn't necessarily abolish it. Some theorists argue that without a true quantum theory of gravity, we're just papering over the problem, like using a bigger bandage on a wound that never healed. This is where loop quantum gravity enters the picture, offering a radical alternative. Unlike inflation, which smooths over the singularity with rapid expansion, loop quantum gravity suggests that spacetime itself is granular, woven from tiny, indivisible loops. At extremely high energies, these loops would resist further compression, causing gravity to become repulsive rather than infinite. The result, a quantum bounce, where the collapsing universe rebounds into expansion without ever reaching a singularity. It's as if the universe took a deep breath at the last possible moment, reversing its own collapse in a cosmic sigh of relief. The implications are staggering. If loop quantum gravity is correct, our universe might not have begun with a bang at all, but with a rebound from a previous cosmos. This cyclical model, sometimes called the Big Bounce, suggests an eternal sequence of expansions and contractions, each leaving subtle traces in the fabric of spacetime. Supporters point to faint anomalies in the cosmic microwave background as potential echoes of this pre-bounce universe, though the evidence remains hotly contested. Yet even this elegant solution has its skeptics. Critics argue that without experimental proof, loop quantum gravity is just another mathematical abstraction, no more verifiable than the singularity it seeks to replace. Meanwhile, inflationary cosmology, for all its unanswered questions, still matches a vast array of observations, from the flatness of the universe to the patterns in the cosmic microwave background. The real tension here isn't just about which theory is right, it's about what science can even hope to explain. Singularities represent the edge of our knowledge, a point where time, space, and causality lose all meaning. Whether we accept inflation's sleight of hand, embrace loop quantum gravity's bold revision, or wait for some third option to emerge, the initial singularity conundrum forces us to confront the limits of our understanding. Because if the birth of the universe remains shrouded in mathematical paradox, how can we ever be sure we're asking the right questions in the first place? Before inflation stretched the universe into existence, there was what a void, chaos, a previous cosmos collapsing in on itself. The truth is, we have no observational evidence, just theories that push the limits of imagination. This is the ultimate cold case, a period so thoroughly erased by inflation's explosive expansion that even light can't carry memories from it. Some physicists picture a quantum foam, a seething ocean where spacetime itself bubbled and frothed at scales 1 trillion times smaller than an atom. In this realm, particles and energy flickered in and out of existence, governed by laws we barely grasp. Others propose a bounce, a prior universe that contracted to a near singularity before rebounding as ours. It's like a cosmic phoenix dying in fire only to be reborn from its own ashes. String theory adds another layer, suggesting higher dimensions curled into invisibility, their geometry seeding our universe's birth. The most unsettling idea, that time itself might not have existed before inflation. Without matter or space, how would clocks tick? How would cause precede effect? Some models treat the pre-inflation era as a mathematical abstraction, a set of equations waiting to crystallize into reality. Yet for all these speculations, one fact remains: inflation acted like a cosmic shredder, obliterating any traces of what came before. The cosmic microwave background, our oldest snapshot of the universe, shows no wrinkles from this primordial past. Gravitational waves from that epoch, if they exist, are too faint for current detectors. Even the laws of physics might have been reset, overwritten like a reformatted hard drive. This isn't just academic curiosity. If we could peer beyond inflation's veil, we might discover whether our universe is unique or one page in an infinite cosmic library. Until then, the pre-inflation era remains the ultimate cold case, its secrets locked behind a barrier we're only beginning to fathom. Here's the cosmic magic trick: no one can fully explain how the fuzzy, uncertain world of quantum mechanics became the crisp, predictable universe we see today. During inflation, space wasn't just expanding. It was a quantum storm where particles and energy flickered in and out of existence in a haze of probabilities. Yet somehow, these ghostly fluctuations hardened into the concrete seeds of galaxies, stars, and planets. This shift from quantum weirdness to classical certainty is one of inflation's deepest unsolved puzzles, and it forces us to rethink reality itself. Picture Schrödinger's cat, that famous thought experiment where a feline is simultaneously alive and dead until observed. Now imagine scaling this up to cosmic proportions. During inflation, the universe was like a cat in a box the size of a galaxy, a place where every particle, every ripple of energy existed in multiple states at once. But unlike the cat, which stays quantum until someone peeks inside, the universe somehow decided its own fate, collapsing all those possibilities into the single reality we inhabit. The question is how. One leading idea involves a process called decoherence, where quantum systems lose their fuzziness by interacting with their environment. Think of it like a spinning coin. While it's in the air, it's both heads and tails, but the moment it hits your palm, friction forces it to choose. Inflation's rapid expansion may have acted like that table, measuring quantum fluctuations by stretching them across spacetime until they froze into classical density waves. Yet even this elegant explanation has holes. Decoherence usually requires an external observer or system to trigger the collapse, but in the early universe, there was nothing outside to play that role. Another theory suggests gravity itself could be the missing piece. Quantum fluctuations were initially so tiny that gravity barely affected them, leaving them in a haze of probabilities. But as inflation stretched these ripples to cosmic scales, gravity's influence grew, forcing them to pick a side. It's as if the universe's own weight pressed down on quantum fog, sculpting it into mountains and valleys of matter. But here's the twist: some regions of space may still be caught between quantum and classical, like cosmic Schrödinger's cats waiting to be observed. Gravitational waves from the early universe, if we can detect them with enough precision, might carry imprints of this transition, hinting at whether it was sudden or gradual, universal or patchy. Until then, this mystery lingers, a reminder that the universe's most fundamental shift, from possibility to reality, might still be hiding in the quantum shadows. We've mapped the cosmic microwave background with breathtaking precision, traced the large-scale structure of galaxies, and even detected gravitational waves, yet all these are just echoes, indirect whispers from the era of cosmic inflation. The smoking gun, direct, undeniable proof, remains frustratingly out of reach. Why is it so hard to catch inflation in the act, and could the next generation of telescopes finally break the silence? The heart of the problem lies in inflation's destructive creativity. Think of it like a cosmic reset button. It stretched space so violently that it erased nearly all traces of its own mechanics. The universe before inflation was scrambled beyond recognition, leaving only subtle fingerprints in the form of density variations and faint gravitational ripples. The cosmic microwave background, our oldest light, is like a photograph taken just after the explosion. It shows the damage but not the detonator. Even the primordial gravitational waves we've hunted for decades are second-hand evidence, vibrations in spacetime's fabric rather than a direct snapshot of inflation itself. Critics argue this indirectness is a weakness, that without observing inflation's engine directly, the theory risks becoming untestable. After all, how do you study a phenomenon that obliterated its own evidence? Supporters counter that this is precisely what makes inflation so powerful. It predicted the CMB's patterns before we observed them, turning what could have been arbitrary noise into a triumph of theoretical foresight. Yet the lingering doubt remains. Could these patterns have alternative explanations like cosmic strings or colliding brains? Enter missions like Lightbird, Japan's upcoming satellite designed to scour the cosmic microwave background for B-mode polarization, a unique twisting of light that could carry inflation's first direct signature. These patterns, if found, would be the curls left behind by gravitational waves generated during inflation's furious expansion. But here's the catch: they're unimaginably faint, buried under interstellar dust and later cosmic events. Detecting them would be like listening for a whisper in a hurricane. The stakes couldn't be higher. Success would cement inflation as one of science's greatest triumphs, while failure might force us to reconsider whether we've been chasing a cosmic mirage. Either way, the hunt for direct evidence isn't just about validating a theory, it's about learning whether the universe's birth left clues we're clever enough to decode, or if some doors to the past are locked forever. In the chaos of the universe's first moments, physicists believed there must have been something pulling the strings, an invisible particle or field that lit the fuse for cosmic inflation. Meet the inflaton, the hypothetical heavyweight champion of the early cosmos. Unlike any particle we've ever detected, the inflaton would have been a quantum puppeteer, its energy driving the runaway expansion of space itself. But here's the kicker: despite decades of searching, no trace of it has ever been found. Not in atom smashers, not in cosmic rays, not even in the faintest whispers of the cosmic microwave background. The inflaton isn't alone in this ghostly menagerie. Theorists have proposed a whole zoo of exotic particles that might have shaped inflation. There's the curvaton, a sneaky sibling thought to have tweaked the density variations in the early universe, leaving behind the lumpiness that eventually grew into galaxies. Then there's the action, a featherweight contender that could have influenced inflation's in-game, like a cosmic timer counting down to reheating. Some models even suggest a spectator field, a passive observer that left subtle fingerprints in the universe's geometry without directly fueling expansion. So where are they? The problem isn't just that these particles are elusive, it's that inflation might have erased them too thoroughly. Think of it like a cosmic crime scene where the perpetrator cleaned up with extreme prejudice. The inflaton, if it existed, likely decayed into the hot soup of particles we recognize today, leaving no intact remnants. Meanwhile, curvatons and actions could be hiding in plain sight, masquerading as dark matter or other known particles, their true origins blurred by 14 billion years of cosmic evolution. The search isn't hopeless, though. Some scientists are scouring the cosmic microwave background for telltale twists in polarization patterns that might betray the inflaton's handiwork. Others are hunting for ultra-rare particle interactions in underground labs, hoping to catch a fleeting glimpse of an action or curvaton. And then there's the radical possibility that these particles aren't particles at all, but higher dimensional vibrations or fragmented echoes of a more fundamental theory we've yet to uncover. The real puzzle isn't just their absence, it's what their discovery would mean. If we found the inflaton, it wouldn't just confirm inflation. It could reveal whether this explosive expansion was a one-time fluke or an endless factory for universes. Each missing particle is a gap in the story, a blank page in the universe's autobiography. And until we fill those gaps, we're left wondering, did inflation's architects vanish without a trace, or are they still here, woven into the fabric of reality in ways we're only beginning to suspect? Hidden within the faint glow of the cosmic microwave background lies a ghostly pattern, one that could either confirm cosmic inflation beyond doubt or send physicists back to the drawing board. Scientists call it B-mode polarization, a twisting in the ancient light that might carry echoes of gravitational waves from the universe's first trillionth of a second. Finding it would be like discovering the fingerprint of inflation itself, but after decades of hunting, this smoking gun remains frustratingly out of focus. The challenge starts with sheer subtlety. These polarized swirls, if they exist, are buried under layers of interference from dust in our own galaxy, gravitational lensing from cosmic structures, and even the afterglow of more recent events like galaxy collisions. Imagine trying to hear a single note from a symphony played at the dawn of time while standing in the middle of a hurricane. This is the noise physicists must penetrate, and the stakes couldn't be higher. Experiments like BICEP have come tantalizingly close. In 2014, researchers at the South Pole announced they detected B modes, only to later realize much of the signal came from galactic dust. It was a cosmic false alarm, one that underscored just how devilishly hard this hunt truly is. The problem isn't just technical, it's existential. If inflation happened at lower energies than predicted, its gravitational waves might be too faint for any telescope to ever detect. Alternatively, if the signal is hiding in a frequency range we haven't probed deeply enough, we might be missing it by sheer bad luck. Yet the search continues with smarter tools and sharper strategies. The next generation of telescopes, like the Simons Observatory and CMB-S4, are deploying armies of ultra-sensitive detectors across multiple frequencies, allowing scientists to subtract galactic dust with surgical precision. These projects aren't just upgrades, they're reinventions, designed to peel back the layers of cosmic static until only the primordial signal remains. But what if, after all this, B modes never materialize? Some theorists argue it wouldn't kill inflation, just force us to rethink its energy scale or mechanism. Others whisper about more radical alternatives, like colliding brain worlds in higher dimensions leaving their own imprints. The irony is thick. A theory conceived to solve the universe's mysteries might itself become one, leaving us to wonder whether the answers we seek are written in the cosmos, or if we've been reading the wrong language all along. Not everyone agrees that cosmic inflation is the slam-dunk explanation for the universe's early moments. Among the most vocal critics is Paul Steinhardt, one of inflation's original architects, who now argues that the theory has strayed from real science into something far less rigorous. His concern: inflation has become so flexible that it can explain almost any observation, making it virtually impossible to disprove. In science, that's a cardinal sin. A good theory isn't just about explaining what we see, it's about ruling out what we don't. Steinhardt's frustration centers on inflation's adaptability. Originally, the theory made crisp predictions. The universe should be flat with specific patterns in the cosmic microwave background. But as observations grew more precise, inflationary models multiplied to accommodate every anomaly. Slightly curved universe, there's an inflation model for that. Unexpected clumpiness in galaxy distributions. Another tweak to inflation can fix it. This chameleon-like quality means that no matter what we discover, inflation can retroactively adjust to fit, raising the question of whether it's truly predictive or just playing cosmic whack-a-mole with data. The scientific response to these criticisms splits into two camps. Defenders argue that inflation's flexibility is a strength, not a weakness, that its core mechanism naturally produces diverse outcomes depending on initial conditions. They point to universal predictions that did hold up, like the CMB's near-perfect blackbody spectrum, as proof inflation isn't just guesswork. Meanwhile, critics like Steinhardt propose radical alternatives, like the Big Bounce, a cyclical model where the universe contracts and rebounds without any inflationary phase. These ideas have their own challenges, but they force physicists to ask harder questions about what evidence would actually settle the debate. At stake is more than just academic turf. If inflation can't be pinned down, if no observation could ever falsify it, then does it belong in the realm of testable science, or is it drifting toward untestable metaphysics? The line between groundbreaking theory and clever storytelling grows uncomfortably thin. Yet for all its flaws, inflation remains the reigning champion because no alternative yet explains the full suite of cosmic clues as elegantly. That uneasy tension between a theory too successful to ignore and too slippery to confirm may linger until new telescopes peer deeper into the primordial universe or until someone devises an experiment that finally tips the scales. Until then, the question hangs, is inflation the key to the cosmos or just a mirror reflecting our own assumptions back at us? One of the most unsettling truths about cosmic inflation is that it appears to break one of physics' most sacred rules, the conservation of energy. Think about it. In a fraction of a second, the universe expanded from submicroscopic to cosmic proportions, creating an incomprehensible amount of matter and energy out of seemingly nowhere. If you could somehow add up all the starlight, galaxies, and dark energy in the cosmos, the total should be staggering, but the math suggests something far stranger. The universe's ledger might actually balance to zero. How? The answer lies in one of Einstein's most counterintuitive insights, gravity's hidden debt. Here's the paradox: energy can't be created or destroyed. It's a cornerstone of physics. Yet inflation blew up the universe like a balloon, filling it with particles, radiation, and eventually galaxies, all brimming with energy. The solution hinges on a peculiar quirk of gravity. It's the only force with negative energy. Picture a skydiver falling toward Earth. As they accelerate, their kinetic energy increases, but the gravitational pull holding them also grows stronger, acting like an invisible negative balance. Cosmologists argue that during inflation, the positive energy of newly created matter was perfectly offset by the negative energy of spacetime's curvature. It's as if the universe took out a gravitational loan to finance its own expansion, a debt etched into the fabric of reality itself. This idea isn't just theoretical. When you calculate the total energy of a galaxy, you'd sum up the mass via E equals mc squared and the kinetic energy of its stars, but then subtract the gravitational binding energy holding it together. For a universe that's flat or nearly so, these numbers cancel out shockingly well. Some models even suggest the total could be exactly zero, a cosmic tab wiped clean by the symmetry of positive and negative. Yet the mystery deepens when we ask where this balancing act begins. Quantum mechanics allows particles to pop into existence briefly by borrowing energy as long as it's repaid quickly. Inflation may have scaled this up catastrophically, stretching virtual particles into real ones while spacetime's curvature footed the bill. But here's the catch: we've never observed negative gravitational energy directly. It's a phantom in the equations, a shadow that keeps the books balanced but vanishes when you look too closely. Critics argue this is a sleight of hand, that calling gravity's energy negative is just a mathematical trick to avoid admitting inflation broke the rules. Others propose wilder fixes, like the universe borrowing energy from higher dimensions or even from its own future. But until we find a way to measure gravity's energy directly, the paradox remains. A universe overflowing with stars, planets, and life might ultimately be built on nothing more than a perfectly balanced cosmic IOU. Cosmic inflation was supposed to be the great equalizer, a process that smoothed the universe into predictable uniformity. But a glaring discrepancy in modern cosmology threatens to upend that tidy picture. Astronomers call it the Hubble tension, two precise but utterly conflicting measurements of how fast the universe is expanding. One method, using the cosmic microwave background as a cosmic yardstick, suggests an expansion rate of about 67 kilometers per second per megaparsec. The other, based on observations of pulsating stars and supernova, insists it's closer to 73. That gap might sound trivial, but in the high-stakes world of cosmology, it's a 5-alarm crisis. If both measurements are correct and repeated experiments keep confirming they are, then something fundamental about our understanding of inflation and dark energy must be wrong. Digging deeper reveals why this tension is so explosive. The CMB method relies on inflation's legacy, the near-perfect uniformity of the early universe, to project how expansion should play out over billions of years. The supernova method, meanwhile, measures expansion directly in our cosmic neighborhood. The fact that they disagree suggests inflation didn't leave the universe quite as uniform as we thought, or that dark energy, the mysterious force accelerating expansion, isn't behaving as predicted. Some theorists propose that dark energy's strength might be increasing over time, a scenario that would force us to rewrite Einstein's equations. Others wonder if unknown particles like sterile neutrinos are tweaking the expansion rate behind the scenes. The most provocative idea, that the Hubble tension is a smoking gun for flaws in inflationary theory itself. Small variations in inflation's duration or intensity could have created regional differences in expansion rates, like cosmic continents expanding faster than others. If true, our corner of the universe might not be representative at all, rendering global measurements dangerously misleading. This would mean inflation didn't erase the universe's wrinkles, it just stretched them beyond our initial perception, leaving hidden fault lines we're only now detecting. Observatories like the James Webb Space Telescope are racing to resolve this crisis, scrutinizing ancient galaxies for clues, but the implications are already seismic. If the tension holds, it could mean that inflation, the cornerstone of modern cosmology, is incomplete, or that we're seeing the first hints of physics beyond our current theories. Either way, the universe is sending us a message. Its expansion isn't just a number. It's a story with chapters we haven't even begun to read. The observable universe stretches over 93 billion light-years from end to end, a scale so vast it defies intuition. Yet buried in that immensity is a paradox. According to standard inflationary theory, the universe shouldn't be this big, at least not in one single continuous expansion phase. The math suggests something startling, that our cosmic neighborhood might be a tiny fraction of a far grander structure, one shaped not by a single burst of inflation, but by multiple crescendos of spacetime stretching. Here's the puzzle. Inflation was designed to explain why distant regions of space look so similar. They were once close enough to exchange heat and information before being violently separated. But the observed uniformity extends far beyond what a single inflationary episode should have reached. It's like blowing up a balloon to the size of a city, then discovering every street corner has identical graffiti despite them being miles apart with no possible connection. Either inflation lasted hundreds of times longer than we thought, or something far stranger was at work. One radical solution: cascading inflation, a scenario where the early universe didn't inflate once, but in waves, like a series of cosmic bellows pumping spacetime larger with each pulse. Each burst would have smoothed its own patch of the cosmos, leaving behind a mosaic of regions with slightly different properties. Our observable universe might just be one bubble in this froth, with others forever beyond our horizon. The implications ripple outward. If multiple inflationary phases occurred, they could explain other cosmic anomalies, like the mysterious cold spot in the CMB, a vast, unusually frigid region that might be a bruise from a collision with another inflating bubble. Even more provocative, these secondary expansions could have tweaked the laws of physics in their domains, creating pockets where gravity is stronger, dark energy weaker, or even where atoms never formed. Critics argue this is overcomplicating a theory already accused of being untestable, but supporters point to mathematical models showing how early quantum fluctuations could naturally trigger staggered inflation like dominoes of spacetime, each tipping the next. Future telescopes might settle the debate by hunting for statistical oddities in galaxy distributions or gravitational wave patterns that betray these layered expansions. The real shock isn't just the scale of our universe, it's the growing suspicion that we're seeing only the first paragraph of a story written in countless volumes. Whether inflation pulsed once or 1,000 times, the message is clear. reality might not just be bigger than we imagined, but more intricate, more layered, and far more mysterious than any single theory can contain. Among the most tantalizing relics of cosmic inflation could be lurking in the darkest corners of the universe, not as stars or galaxies, but as ancient black holes forged in the furnace of the universe's first moments. These aren't the black holes we know today, born from collapsing stars. These would be primordial, stitch marks in the fabric of spacetime itself, sown by the violent density fluctuations of inflation. And if they exist, they could rewrite everything we know about dark matter, galaxy formation, and the fate of the cosmos. Picture this: during inflation, some regions of space were stretched so violently that matter became crammed into knots of unimaginable density. These knots wouldn't just form stars, they'd skip straight past that stage, collapsing directly into black holes, some as small as an atom, others as massive as 1,000 suns. Unlike their stellar descendants, these primordial black holes wouldn't need the death throes of a star to exist. They'd be cosmic orphans wandering the universe since before the first light dawned. The hunt for these ghosts has turned up empty so far, but their potential fingerprints are everywhere. Some scientists argue they could solve the dark matter enigma, that the universe's missing mass might be hiding in plain sight as countless invisible black holes. Others suggest they could explain bizarre gravitational wave signals, like the unexpectedly heavy black holes detected by LIGO, which seem too massive to have formed from stars in the time available. Yet the lack of definitive proof cuts both ways. If primordial black holes are everywhere, why haven't we seen their telltale microlensing effects, the way their gravity bends light from distant stars? Why do some calculations suggest they'd have evaporated by now, thanks to Hawking radiation? The answer might lie in their size. Tiny black holes, those smaller than a mountain, would have radiated away their mass long ago. But larger ones, those heavier than an asteroid, could still be out there, invisible yet omnipresent. The stakes are cosmic. Finding even one primordial black hole would confirm that inflation's wild quantum fluctuations could warp spacetime into permanent scars. It would mean our universe is seeded with artifacts from its very first breath, relics so old they predate time as we know it, and if they're not there, that absence would force us to rethink just how chaotic inflation truly was, or whether we've been searching for shadows while missing the real monsters lurking in the dark. The numbers behind cosmic inflation don't just intrigue scientists, they border on the unbelievable. For inflation to create a universe like ours, its initial conditions had to be fine-tuned with precision that defies probability. Imagine balancing a pencil perfectly upright on its tip, not just for a second, but for billions of years. Now scale that impossibility up to cosmic proportions, and you begin to grasp the staggering unlikelihood of our universe's birth. Take the inflatoned field, the hypothetical engine behind expansion. Its energy density had to be exactly right, too strong, and space would have ripped apart before matter could form, too weak, and gravity would have crushed the nascent universe back into nothingness. Calculations show that varying this value by just 1 part in 10 to the power of 15 would have rendered our existence impossible. Similar razor's edge requirements govern the rate of expansion, the timing of reheating, even the quantum fluctuations that seeded galaxies. It's as if someone dialed in 1,000 cosmic knobs to impossible settings all at once. This eerie perfection fuels one of cosmology's fiercest debates. Some argue it points to a multiverse, a vast ensemble of universes where ours is just the lucky lottery winner. Others see it as evidence of something deeper, perhaps even intentional. Theologians and philosophers have seized on this fine-tuning as modern evidence for a designer, while scientists like Leonard Susskind counter with the anthropic principle. We observe these precise values simply because they're the only ones that allow observers to exist. Yet both explanations leave physicists uneasy. The multiverse, while mathematically plausible, pushes key evidence beyond observational reach. the anthropic principle feels like surrender answering why with because. Even more troubling, some fine-tuning appears unnecessary. Certain parameters could vary widely without preventing life, yet they're pinned to specific values anyway. It's like finding a safe with a 1,000-digit combination lock, only to discover most digits could be anything but were set precisely regardless. New theories attempt to sidestep the problem altogether. Conformal cyclic cosmology suggests our universe's fine-tuning was inherited from a previous eon's death. Quantum gravity models propose that what we see as fine-tuned constants might be emergent properties like temperature arising from atomic motion. But until these ideas produce testable predictions, the mystery persists, a cosmic riddle written in mathematics so exact it feels like a message. Whether the answer lies in physics, metaphysics, or something beyond both, one truth remains: our universe's birth wasn't just unlikely. It was, by any reasonable measure, almost impossible. At the furthest edges of theoretical physics, where even the wildest ideas about cosmic inflation start to sound tame, there exists a class of models so radical they make faster-than-light travel look pedestrian. These are the superluminal inflation theories, speculative blueprints suggesting that the universe didn't just expand faster than light during inflation, but that some regions of space-time may have ripped apart so violently they shattered causality itself. If proven true, they wouldn't just rewrite cosmology, they'd force us to toss out Einstein's speed limit entirely. So why do serious scientists still toy with these phantom models? The answer lies in a stubborn mismatch between theory and observation. Standard inflation does an excellent job explaining the universe's large-scale smoothness, but when you zoom in, certain anomalies refuse to fit. Some patches of the cosmic microwave background show statistical quirks, slight over densities, or unexpected alignments that conventional models struggle to account for. Enter superluminal proposals, which posit that inflation wasn't a uniform process but a fractured one, with isolated pockets where spacetime's expansion went into hyperdrive. Picture a pot of water boiling. Most bubbles rise at a steady pace, but occasionally one bursts forth with explosive force. In these models, those rogue bubbles could have stretched space so fast that quantum fluctuations froze into patterns unlike anything our standard theories predict. The most extreme version of this idea is called superluminal bubble nucleation, where patches of the inflattened field tunneled through energy barriers, creating temporary pockets where expansion rates approached infinity. The implications are mind-bending. Regions caught in these bubbles wouldn't just be far apart, they'd be fundamentally disconnected from our causal history, like islands floating in a sea where time flows sideways. Some theorists argue this could explain the infamous axis of evil, a strange alignment of anomalies in the CMB that seems to defy statistical randomness. If a superluminal bubble brushed against our observable universe, it might have left behind a cosmic fingerprint we're only now deciphering. Of course, these models come with heavy baggage. Breaking the light-speed barrier isn't just a technicality, it threatens to unravel relativity's core principle that cause must precede effect. Yet there's a loophole. While nothing can move through space faster than light, spacetime itself has no such restriction. Inflation already exploits this by stretching space between objects, not moving them. Superluminal models take this further, suggesting that under extreme conditions, space could have fractured into domains where local physics operated by different rules. It's not so much breaking the speed limit as it is rewriting the road. Critics dismiss these ideas as mathematical fantasy, arguing that without observable consequences, they're little more than clever equations in search of reality. But supporters counter that we may already have seen hints, not just in the CMB, but in the puzzling way certain ultra-high-energy cosmic rays behave. If future telescopes detect gravitational wave patterns that match these models' predictions, it could force a reckoning with one of physics' most sacred cows. Until then, these phantom theories linger in the shadows, daring us to imagine a dawn of time far stranger than we ever thought possible. At the heart of cosmic inflation lies a silent chasm, a gap so profound it shakes the very foundations of physics. For all its explanatory power, inflation's machinery grinds to a halt when we approach the Planck scale, that unimaginably tiny realm where quantum fluctuations warp spacetime itself into a seething foam. Here, gravity ceases to play by the rules we know, and our equations dissolve into chaos. This is the quantum gravity void, the black hole in our understanding where inflation's most critical moments remain shrouded in mystery. Think of it like constructing a skyscraper without knowing the properties of steel. Inflation's equations beautifully describe how space stretches and matter forms, but they rely on assumptions about gravity's behavior at energies a trillion times beyond what we've ever probed. At these scales, spacetime isn't the smooth fabric of Einstein's relativity. It's a turbulent quantum storm where wormholes blink in and out, dimensions fray, and cause and effect might not even apply. Inflation's entire mechanism, the inflated fields, roll down its energy landscape. The transition to the Big Bang depends on physics we simply don't possess. This void manifests in startling ways. Take the singularity problem. Inflation pushes the Big Bang's infinite density into the past, but without quantum gravity, we can't say whether it truly erased the singularity or just hid it behind a mathematical curtain. Similarly, the reheating phase, when inflation's energy transformed into the particles of the hot Big Bang, requires quantum gravity to explain how spacetime's violent stretching coughed up matter without tearing reality apart. Even inflation's vaunted predictions, like the spectrum of cosmic microwave background fluctuations, ultimately trace back to quantum fluctuations amplified by gravity's hand, a hand whose grip we've never fully seen. The stakes couldn't be higher. If quantum gravity operates differently than we've guessed, inflation's entire story might unravel. Some loop quantum gravity models, for instance, suggest spacetime's granular nature could have prevented inflation from ever starting, replacing it with a quantum bounce from a prior universe. String theory, meanwhile, hints that extra dimensions could have altered inflation's dynamics in ways we're only beginning to fathom. Without experiments that probe the Planck scale, something far beyond today's particle colliders, we're left with a theory built on shadowy foundations. Yet this void isn't just a barrier, it's a beacon. The fact that inflation's predictions align so well with observations despite resting on unknown physics suggests we're glimpsing something fundamental. Perhaps future gravitational wave detectors will catch whispers of Planck-scale phenomena frozen into the universe's earliest moments. Or maybe anomalies in the CMB's polarization patterns will reveal quantum gravity's fingerprints. Until then, the quantum gravity void remains both inflation's greatest weakness and its most thrilling frontier, a reminder that the cosmos's deepest truths often lurk just beyond the edge of our understanding. What if inflation never truly ended, not just in some distant bubble universe, but right here in our own cosmic backyard? This is the spine-tingling premise of the endless inflation scenario, where the runaway expansion that birthed our universe continues its relentless march in hidden pockets of space, even as you watch this video. Far from being a one-time event, inflation could be an eternal cosmic force, endlessly birthing new realities with every passing instant, each operating under radically different physical laws while remaining forever beyond our reach. The math behind this idea is as elegant as it is unsettling. In most inflationary models, the inflated field, the hypothetical energy driver of expansion, eventually loses steam, decaying into the particles that fueled the Big Bang. But under certain conditions, this field could remain stuck in a high-energy state in some regions, like a rolling ball trapped on a plateau, while inflation ends in our local bubble, allowing galaxies and stars to form. Neighboring regions continue stretching exponentially, spawning new bubbles where the process repeats. The result, a fractal multiverse, where islands of stability like ours float in an ever-growing sea of inflating spacetime. Some of these distant bubbles might harbor physics unrecognizable to us, universes where gravity is 1,000 times stronger, where light moves at a snail's pace, or where atoms never coalesce. Others could be nearly identical to ours with only subtle variations, perhaps a slightly heavier electron or a weaker nuclear force. The terrifying beauty of eternal inflation is that it renders all possibilities inevitable given enough time and space. There could be realms where time flows backward, where entropy decreases instead of increases, or where black holes are as common as stars. Yet for all its grandeur, this model poses a brutal challenge for science. If these regions are forever inflating beyond our cosmic horizon, how could we ever detect them? Some theorists hunt for bruises in the cosmic microwave background, anomalous cold spots or strange polarization patterns that might betray collisions with other bubbles. Others speculate that gravitational waves from the early universe could carry imprints of neighboring inflating domains. But the most haunting possibility is that no evidence will ever surface, leaving eternal inflation as an idea too vast to prove and too compelling to ignore. The implications claw at the edges of rationality. If inflation is truly endless, then the universe we call home is just a temporary eddy in an infinite cosmic river, destined to one day find itself surrounded by inflating space that will stretch all other galaxies beyond visibility. Even more unsettling, this process might not be rare. Calculations suggest that in an eternally inflating multiverse, the volume of space undergoing inflation grows exponentially over time, meaning most of reality would consist of empty, rapidly expanding voids, with stable bubbles like ours becoming vanishingly rare. This isn't just theoretical gymnastics. Eternal inflation forces us to confront whether the laws of physics are truly universal or merely local bylaws in our cosmic neighborhood. It suggests that the constants we consider fundamental, the speed of light, the strength of gravity, might be accidents of geography, frozen into our region of spacetime while other domains play by entirely different rules. And if that's true, the ultimate question isn't just why does our universe exist, but why does it exist this way? A mystery that might never have a single answer, only an infinity of alternatives playing out across the unobservable reaches of reality. Buried in the afterglow of the Big Bang lies a cosmic oddity so bizarre it's been dubbed the axis of evil, a sprawling cold spot in the cosmic microwave background that defies all expectations. Stretching nearly 2 billion light-years across, this region is cooler than its surroundings by a mere fraction of a degree, but that subtle dip has sparked a firestorm of debate. Is it a relic of inflation's quantum chaos, a statistical mirage, or something far stranger, like a bruise from a collision with another universe? The cold spot first emerged in data from NASA's Wilkinson microwave anisotropy probe, and later observations by the Planck satellite only deepened the mystery. Ordinarily, temperature variations in the CMB are like static random noise with predictable patterns, but this spot is an outlier, chillingly improbable under standard inflationary models. The odds of it appearing by chance, less than 1 in 50. It's as if you shuffled a deck of cards and drew the same royal flush 3 times in a row, possible, but enough to make you suspect the deck is rigged. Proponents of exotic physics pounced. One radical theory suggests the cold spot is a texture, a twisted knot in spacetime left behind when the universe's fundamental forces split apart during inflation. Think of it like a cosmic version of frozen in stress lines in glass, an artifact of the universe's rapid cooling. Others argue it could be evidence of a collision with another inflating bubble universe, a scenario straight out of the multiverse playbook. In this view, our universe might have bumped into a neighboring realm during its earliest expansion, leaving behind a gravitational shadow visible in the CMB's chill. Yet skeptics counter with Occam's razor. Maybe the cold spot isn't a cosmic smoking gun, just an unlucky roll of the dice. The CMB contains trillions of pixels. Some statistical anomalies are inevitable. Simulations show that even in perfectly uniform inflationary models, a few rogue cold patches can emerge purely by chance, and alternative explanations abound. Perhaps it's a vast cosmic void, a region unusually devoid of galaxies, bending light in ways that mimic a temperature drop. Or maybe it's an artifact of foreground interference, dust in our own galaxy casting a deceptive shadow. The controversy cuts to the heart of how we do science. When is an anomaly worth chasing, and when is it just noise? The cold spot's sheer scale makes it hard to ignore, yet proving its origins is like reconstructing a crime scene 14 billion years cold. Future telescopes, like the Simons Observatory, aim to scrutinize the spot's polarization patterns, a potential Rosetta Stone for distinguishing between mundane explanations and universe-shattering ones. If the polarization twists in a specific way, it could signal a primordial texture or bubble collision. If not, the cold spot might fade into the annals of cosmic curiosities. What makes this enigma so gripping isn't just the science, it's the philosophical tension beneath it. The cold spot represents a choice. Do we dismiss outliers as statistical ghosts, or embrace them as clues to a reality far weirder than we imagined? Inflationary theory is robust but not infallible. Every anomaly, every stubborn data point is a chance to ask, what if we've been missing something fundamental all along? Whether the cold spot is a flaw in our maps or a crack in our theories, its greatest lesson might be humility. The universe, after all, has a habit of surprising those who claim to know its secrets. Science thrives on evidence, the ability to test, probe, and challenge ideas until they stand or fall. But cosmic inflation now faces a quiet rebellion from within the scientific community, as whispers grow louder that its grand claims might never face the scrutiny of direct proof. This isn't just academic squabbling, it's a crisis that threatens to blur the line between groundbreaking science and untestable speculation. If inflation can't be pinned down with definitive evidence, does it belong in the realm of physics, or does it slip into something closer to metaphysics? The heart of the problem lies in inflation's elusive nature. Unlike black holes, which reveal themselves through gravitational waves and glowing accretion disks or dark matter, whose presence bends light and tugs on galaxies, inflation left behind only indirect traces, subtle patterns in the cosmic microwave background, the large-scale arrangement of galaxies. These echoes are compelling, but they're also open to interpretation. Different models of inflation can tweak their parameters to match almost any observation, like fitting a key to multiple locks. The result, a theory so flexible it risks becoming unfalsifiable, a cardinal sin in science. Critics like physicist Paul Steinhardt, who helped pioneer inflation only to become its most vocal skeptic, argue that the theory has morphed into a theory of anything. When observations didn't perfectly match initial predictions, inflation adapted. Too much curvature in the universe adjusts the inflated field's potential. Not enough galaxy clustering, tweak the quantum fluctuations. This adaptability, while impressive, means inflation can explain nearly any outcome, making it nearly impossible to disprove. In science, a theory that can't be falsified isn't a theory at all. It's a narrative. The stakes are existential. If inflation remains forever beyond direct verification, it could set a dangerous precedent, allowing untestable ideas to masquerade as settled science. Some researchers counter that indirect evidence still counts after all. We accept the existence of dinosaurs despite never observing them directly, but the comparison falters under scrutiny. Fossils leave tangible, physical traces. Inflation's fingerprints are statistical, woven into the fabric of probabilities. Without a smoking gun, like primordial gravitational waves etched into the CMB's polarization, the theory floats in a limbo of plausible but unprovable conjecture. Yet hope isn't lost. Next-generation experiments like CMBS-4 and space-based gravitational wave detectors aim to probe inflation's aftermath with unprecedented precision. If they find the telltale swirls of B-mode polarization or primordial ripples in spacetime, inflation could solidify its place as cosmology's crowning achievement. But if these searches come up empty, the scientific community faces a brutal choice: cling to an elegant but unprovable idea, or abandon it in favor of something radically new. The testability crisis forces us to confront an uncomfortable truth: that some of the universe's grandest mysteries might forever lie beyond our reach. Whether inflation survives this reckoning or fades into history, its greatest lesson may be humility. The cosmos owes us no answers, and our hunger for understanding must sometimes wrestle with the limits of what we can ever know. From the trigger that ignited cosmic inflation to the ghostly absence of magnetic monopoles, from the universe's eerie flatness to the multiverse's infinite possibilities, these 25 mysteries aren't just gaps in our knowledge. They're threads in a grand cosmic tapestry, each one woven into the fabric of reality itself. Every unanswered question, every unsolved riddle is a doorway to discovery, a challenge that pushes science forward. Take the Hubble tension, that stubborn mismatch in how fast the universe is expanding. It's not just a numbers game, it's a clue that our understanding of dark energy or even inflation itself might be incomplete. The cold spot in the cosmic microwave background, it could be a statistical fluke or a cosmic bruise from a collision with another universe. Even the missing inflaton particle, if found, wouldn't just fill a gap in a textbook. It could reveal whether our universe was a one-time miracle or an inevitable outcome of deeper laws. What's remarkable isn't just the scale of these mysteries, it's how they connect. The quantum gravity void ties into the initial singularity problem, which loops back to eternal inflation and the multiverse. The fine-tuning of the universe's constants might hinge on whether inflation was a single event or part of an endless cycle. These aren't isolated puzzles, they're pieces of a single, sprawling enigma, and solving one could unlock them all. But here's the real magic: these questions aren't just for physicists. They're for anyone who's ever looked up at the night sky and wondered how or why. Because the answers won't come from telescopes and equations alone. They'll come from curiosity, from daring to ask the next question, from refusing to accept "we don't know" as the final word. So stay curious, keep questioning. The next breakthrough might not come from a lab or a supercomputer, it might come from you. After all, the universe didn't give up its secrets easily 14 billion years ago. Why should it start now?